Lesson 2. Insertion sort. The insertion sort is somewhat similar to the bubble sort in that we compare adjacent entries and swap them if they are out of order. Unlike the bubble sort, however, we don't require that we find the next largest or smallest element. Instead, we take our next element and insert it into the sorted list that we maintain at the beginning of the array. In this example, we will use an array for illustration. However, the algorithm works for other types of linearly sorted structures such as linked lists. We use white to indicate the elements that have already been sorted, and a light gray to indicate the element that is being inserted. Beginning the insertion sort, we can consider the first element as our starting sorted list. Since there is only one element, we can consider it sorted. Then we move to the second element and compare to the first. If they are out of order, we swap them. Otherwise, we leave them alone. At this point, the first two entries comprise our sorted list. We then go on to insert our third entry and so on. In general, we insert each successive element by swapping it with the one before it until we reach a smaller element. Now we'll demonstrate the insertion sort on an array of integers. At any stage, the insertion sort has a set of sorted elements and an element that is to be inserted. We begin with the first element equal to 24. Since this is only one element, we consider it a sorted list of length 1. Next, we insert the element 13, which is in the second place. Comparing 13 and 24, we see that they are out of place, so we swap them. Now we have a sorted array of two elements. We move on to insert the third element, which is 9. Comparing 9 to 24, we see that they are out of order, so we swap them. Then we compare 9 to 13. Since these are out of order, we swap them also. Now we have a sorted array of 3 elements. We move on to insert the fourth element, which is 64. Comparing 64 to 24, we see that the elements are in order, so our fourth element is already in its proper place. Now we have a sorted array of 4 elements. Going on to insert the fifth element, we have a 7 there. Comparing this element to 64, we see that they are out of order, so we swap them. In fact, 7 is the smallest element so far, so we'll move all the way up to the beginning of the array. Now we have 5 sorted elements. Moving on to the sixth element, we have 23. This is smaller than 64 and 24, so it gets inserted before those. With 6 sorted elements, we move on to the seventh, which is 34. 34 is smaller than 64, but bigger than 24, so it gets inserted between them. Now we have all of the elements sorted except the last one, which is 47. After 2 comparisons and 1 swap, the entire array is sorted. Insertion sort has an advantage over bubble sort in that we only need to make comparisons until we find the location of the element in the sorted list. This means that unless the array is totally backward, we will make fewer comparisons than bubble sort, and if our array is already sorted, we will only make n comparisons. A convenient aspect of the insertion sort is that the method can be used to add new elements to a sorted array at any time. In fact, this is how you will most often see insertion sort used in practice. We will give an analysis of the time complexity for insertion sort later. For now, we will just give the pseudocode for the algorithm. We begin with a for loop that loops over the index of the entry that is to be inserted. Then we run through a while loop that performs the insertion. The while loop swaps the inserted element with the one before it as long as it is less. This concludes